assignment. But you don't have to turn it in. The homework that require you to watch the video file, the video on the YouTube. This link is going to give you the video file on YouTube about chip manufacturing. Okay? Not really long, probably around like 15 minutes or so. 它不是很长的片，就大概15分钟或者就可以看完。That video probably more helpful for you to understand the real chip manufacturing. And although it's not required that you have to clean it, you have to like it's going to be your exam material. The written exam is going to cover that video file, that video. Okay? Is that clear? So you have to watch it at home. But we can try to look at that a little bit. 这是晶面设计、晶面制造的影片，那请大家自行回家去看。那我们现在可以稍微再看一听。So let's watch a little bit the video. 给大家看一下它是什么东西。
All chips start out with a very simple raw material, sand. Sand is primarily made up of silicon dioxide, or silica. Silicon is the second most abundant element in the Earth's crust, but is only ever found as a compound with oxygen. Complex chemical and physical processes are required to ensure that silicon crystals meet the high production standards that apply to chips. To convert silica sand to silicon, the sand is combined with carbon and heated to an extremely high temperature to remove the oxygen. A number of other steps are required to create the finished product, namely an extremely pure monocrystalline silicon ingot called a boule, with only one impurity atom for every 10 million silicon atoms. Silicon boules are fabricated in a range of different diameters. The most common sizes are 150, 200, and 300 millimeters. Wafers with large diameters offer more space for chips. Extremely thin wafers are then cut from the silicon boules using a special sawing technique. These wafers are the basic building blocks for subsequent chip production. Silicon is a semiconductor. This means it can conduct electricity and also act as an insulator. Its atomic structure looks like this. Every silicon atom has 4 outer electrons. There are no free charge carriers. As a result, the pure monocrystalline silicon is non-conductive at room temperature. To allow it to become conductive, small quantities of specific atoms are added as impurities to the wafer. These impurity atoms must have a number of outer electrons that is either one more or one less than that of silicon. Silicon is in the 14th group of the periodic table of elements. This means that elements in the 13th or 15th group have to be used in this process, referred to as doping. Boron and phosphorus atoms are the most suitable elements in these groups. They are very close to silicon on the periodic table and therefore have very similar properties. Phosphorus has 5 outer electrons. When it is inserted into the silicon crystal lattice, the 5th phosphorus electron can move freely. This means that the silicon phosphorus crystal is N-conductive. In contrast, boron atoms only have 3 outer electrons. When they are introduced into the silicon lattice, one silicon electron has nothing to bond to. This creates electron holes. The holes move through the crystal like positively charged particles, making the material p-conductive. Transistors are built on the P and N conductive layers that exist in a doped wafer. Transistors are the smallest control units in microchips. Their job is to control electric voltages and currents, and they are by far the most important components of electronic circuits. Every transistor on a chip contains P and N conductive layers made of silicon crystals. They also have an additional layer of silicon oxide, which acts as an insulator. A layer of electrically conductive polysilicon is applied on top of this. Every transistor has 3 terminals. The middle one is attached to the gate, which is the electrically conductive polysilicon. If an electrical charge is applied to only the 2 outer terminals, electricity cannot flow as the transistor is blocked. This changes, however, if an additional charge is applied to the middle terminal. Electrons from the P layer are then pulled toward the middle terminal and accumulate at the area bordering the silicon crystal and the insulating gate oxide. A channel then forms underneath the gate between the islands of N-conductive material. Electrons can now flow through this channel. The electrical circuit is closed. In this way, the transistor can be switched back and forth between current enabled and disabled, between 0 and 1, on and off. But how are these layers created on a wafer? The process to manufacture chips from a wafer starts with the layout and design phase. Highly complex chips are made up of billions of integrated and connected transistors, enabling sophisticated circuits such as microcontrollers and crypto chips to be built on a semiconductor surface measuring just a few square millimeters in size. The sheer number of components calls for an...
I thought I'd just watch a little bit, but I think it's a good video and that's very long, so let's try to complete it, okay? Yeah, it's a good video.
In-depth design process. This entails defining the chip's functions, simulating its technical and physical properties, testing its functionality, and working out the individual transistor connections. Special design tools are used to draw up the plans for integrated circuits and develop a 3-dimensional architecture of sandwich layers. This blueprint is transferred to photomasks. Providing geometric images of the circuits, the photomasks are used as image templates during the subsequent chip fabrication process. To ensure that the microscopic structures of a chip are reproduced flawlessly, they have to be fabricated in a dust-free environment with stable temperature and humidity levels. In other words, they have to be made in a clean room. A clean room is a room in which no more than 1 particle of dust larger than 0.5 micrometers is permitted in around 10 liters of air. This is even cleaner than the air in an operating room. The ventilation, filtration, and supply systems in a clean room therefore have to be extremely sophisticated. Several million cubic meters of air are circulated every hour, and hundreds of air volume regulators maintain a constant airflow. Employees in these production areas have to abide by an extremely strict dress code. They are not permitted to smoke before work or wear any makeup or jewelry. Clean room production areas can only be accessed through a special airlock. Chips are built on a base wafer cut from a silicon pool. Depending on their size, several dozen or several thousand chips can be fabricated on one wafer. First of all, the surface of the wafer is oxidized in a high-temperature furnace operating at approximately 1,000 degrees Celsius to create a non-conductive layer. Then a photoresist material is uniformly distributed on this non-conductive layer using centrifugal force. This coating process creates a light-sensitive layer. The wafer is then exposed to light through the photomask in special exposure machines known as steppers. During this process, coaster-sized areas of the chip template, known as reticles, are used to transfer the complex geometric patterns of the circuit design to the silicon wafer. The exposed area of the chip pattern is developed, revealing the layer of oxide below. The unexposed part remains as is, protecting the layer of oxide. After this, the exposed layer of oxide is etched off in the areas that have been developed using wet or plasma etching. With plasma etching, special gases bond with the substrate to be removed in the reaction chamber. This enables microscopic layers to be removed in the windows that were exposed and developed in the previous step. Once the photoresist residue has been stripped and the wafer has been cleaned, the wafer undergoes further oxidation. Electrically conductive polysilicon is deposited on this insulation layer. Then photoresist is applied again, and the wafer is exposed to light through the mask. The exposed photoresist is stripped again. Now the polysilicon and the thin oxide layer are etched off. These two layers only remain intact in the center under the photoresist. The next step is the doping process, where impurity atoms are introduced into the exposed silicon. An ion implanter is used to shoot impurity atoms into the silicon. This changes the conductivity of the exposed silicon by fractions of a micrometer. After the photoresist residue has been stripped, another oxide layer is applied. The wafer undergoes another cycle of applying photoresist, exposure through the mask, and stripping. Contact holes are etched to provide access to the conductive layers, enabling the contacts and interconnections to be integrated in the wafer. This is done by depositing metal alloys onto the wafer in sputtering machines. Once again, the photoresist and mask are applied. The unexposed strips remain as is after the etching process, providing a point of contact to the underlying layers. To give the insulation layer above the interconnections the smooth finish it requires, a chemical-mechanical process is used to polish away excess material with micrometer accuracy. These individual steps may be repeated multiple times in the fabrication process until the integrated circuit is complete. Depending on the size and type of chip, the wafer will now contain anything from several dozen to thousands of chips. Individual chips are usually sawed out of the wafer. The chips are not lined up flush with each other on the wafer because tiny parts of the wafer splinter off during the sawing process. A certain amount of space, known as the scribe line, is always left between the individual chips. Test structures are also integrated in the space between the chips and used to take measurements immediately after production. These test structures are destroyed during the sawing process. The size of the resulting chips typically varies between 1 square millimeter and a few square centimeters. The final stage of fabrication is assembly. Here, the individual chips are placed in a package and terminals are attached. The result is a finished semiconductor device, which can be mounted on circuit boards using different types of terminals. Over 1,000 connection contacts can be realized. Here are some examples of ready packaged semiconductor components. Special larger packages are used for power semiconductors, intended for applications such as trains, electric cars, solar panels, and wind turbines. These power semiconductors are designed to switch electrical currents of up to several hundred amps and voltages that run into the thousands. Switching at this level generates high temperatures, and this heat has to be dissipated via cooling areas integrated into the packages. Here you can see some fully packaged power semiconductors. Cutting-edge technology is used for testing at every step in the fabrication process to ensure the highest quality levels and chip yield. Researchers and developers use scanning electron microscopes to repeatedly check the chips at different points in the production process. If we compare today's microelectronics with human hair, we can see just how small these devices are. The equipment used to check components and analyze defects is just as precise. These high levels of precision and quality are essential at every stage of the workflow, from the production of silicon boules through the cleaning room fabrication to quality control, in order to deliver these tiny building blocks that have such a big impact on our lives, today and in the future. After all, demand is rising for innovative semiconductor solutions that make life easier, safer, and greener. For technology that achieves more, consumes less, and is available to everyone. Microelectronics is the key to a better future. Part of your life, part of tomorrow. Infineon.
Okay. Good video. So, you want to review it at home. Now let's get back to the rectifier. Okay, as I said, you have to follow the design rule of a specific process, like this one. You will define that how wide for each layer and what is the minimum spacing between the same layer, so forth. Any question? So let's take the inverter as an example. Again, inverter, transistor dimension specified as width over length. If there's some number around the transistor, like 8/2, 4/2, what does it mean? It means that this transistor, the channel length is 2. That's the minimum channel length, 2 lambda. Okay, 8 lambda or 4 lambda is the channel width. How wide in the polysilicon. Okay? So you can see that, so this is 2 lambda. The width, the channel length is 2 lambda. The width, the channel length, 2 lambda. The width is 8 lambda wide, 4 lambda wide. Okay, the channel width. You might wonder the contact, the black bar here, okay? If your diffusion is wider than the minimum width of the diffusion there, it's going to be a rectangular for the contact, but indirectly it's going to be cut into several black bars. You can also denote the transistor size only given the integer, either 2 or 1. That indicates that 1 is the minimum transistor, minimum size, 最小的transistor. Now, 放电池，这边缺一个 battery. All right. As I said, it's an inverter. That's okay. This is an inverter, and the input by the output. The PMOS transistor, is VDD, is ground. And the circuit figure, let's say 2 is 2 lambda, indicating the transistor channel length. So 2 is the minimum transistor channel length. And 8 and 4 are the channel width, respectively. How wide of the transistor. You can also denote that 2 for 8 over 2, 1 for 4 over 2, because 4 over 2 is the minimum size of the transistor. When we say 2 indicate double width. Okay? Channel length is still minimum, but we double the width. The channel width indicate that double the size. And that's quite popular that we not necessarily we have to use the minimum size transistor. No, not always. But sometimes it could be wider than minimum channel width. Why is that? For the inverter, it's very popular because the MO transistor, typically even the same size, MO transistor is going to be faster than PMOS transistor. When I say faster, means that you switch off, is going to be faster than the PMOS transistor, even the same size. Why is that? Because the mobility of electron is different from the mobility of the hole. From physics class, we know that the mobility of the electron is higher than the mobility of the hole. Okay? It's about double the mobility compared to the hole. So that's why, because for MO transistor, the current is negative current, is electron goes through the channel. For PMOS transistor, it's hole goes through the channel. And because it's easier for the electron moving around in the circuit. So you try to make the PMOS transistor wider to allow more current going through on the material. Is that clear? 我们让 PMOS transistor 呢2倍的宽度 because the mobility of the PMOS transistor is only 1/2 of the mobility of the electron. So when we make that double width wider than PMOS transistor, you're going to let the potential current, the hole, going through the material to compensate the mobility, only 1/2. In this case, you're going to get the same speed of the transistor for PMOS and NMOS transistor. So, given the same size, let's assume that both are minimum size, 4 lambda over 2 lambda, then 1. Then the input from low to high, and then from high to low. The output is going to be from high to low, and then from low to high, right? Inverter. Just reverse it, right? When the input is low, the output is high. When the input is high, it's low. Input is low, it's high. That's inverter. But because of the transistor, PMOS transistor, NMOS transistor, the circuit speed is different because of the mobility of electron versus hole. Can you tell me which one is faster? High to low or low to high? Because they're slow, actually. It's slow. Okay, not very accurate. It's not really steep. It's kind of slow. But can you tell me which one is faster? Which one is deeper? from high to low or from low to high, based on the characteristic of pivot to delay pivot to delay。你可以告诉我，这个 inverter 呢，它是从 output 端从1变到0，也就是从0到1在 input， 或者从0到1，哪一个比较快 ？Take this time to reach the final value 0, 1. Which one is faster? Any? Yes. High to low is faster or slower? Faster, right? Okay. The answer is correct. Why is that? So it means that from high to low is going to be faster. It's steeper. And from low to high is going to be slower. Something like that. Why is that? Let's say MO transistor switching from high to low, from low to high. When input from low to high, signal 1 is going to turn on MO transistor, right? And PMOS is going to turn on. And because MO transistor is faster, so you are getting to low voltage level faster within using less time to reach the final value. On the other hand, PMOS is slower, so it's going to be slow for you to switch on from low to high. Okay? And that related to the mobility of the electron and hole. Because when you have good mobility for electron, it's going to move faster in the channel. So it's going to be consume less time to turn on the switch. Okay, that's the idea behind the circuit. All right. So let me give you another example. How about this? So let's say if you have wire for PMOS transistor, then more hole goes through, right? Double the number of the hole goes through the transistor. So that will compensate your circuit speed. How about this? Two input NAND gate. The two input NAND gate. The VDD, the ground. A input connected to this PMOS and this PMOS. B input connected to this PMOS and this PMOS. And then, can you tell me what is going to be the size for each transistor, such that you can get the same switching speed from low to high, high to low. The idea is similar, but it's more complex in this example. We can compare the switching speed for the output 0 to high or high to low, or 0 to 1 or 1 to 0. We are taking the minimum, the conservative point of view, meaning the worst case. For the worst case, given different combination of the input, 1 1 0 0 1 0 0 1. Taking the pessimistic case, what is the output switching 0 to 1 1 to 0? if they are both the same speed, what is going to be your transistor size for 59? Can you tell me? One is the minimum. Minimum channel length, also minimum channel width. Two is double the width, also minimum channel length. To compensate, how about two input link gate? Any suggestion? You have answer? Four. Okay, let me try to put down. Four is the size of transistor or the channel width. The ratio over 2. Okay, so 4 over 2, right? Is that what you mean? No. The 4 times of the channel width. Okay. And the MOS transistor? 1, all right. There's one possible answer. How about something else? 有没有其他的看法 ？Any other situation? 有别的答案 ？Any answer? Okay. PMOS 2, okay. How about NMOS? 1? Okay. What else? 还有没有别的答案？ Okay, I'm going to give you the answer. Actually, no, not 4, not 2. They are all 1. 都是1，都是最小的。They are all minimum size transistor. Why is that? Okay, we are talking about the worst case. From low to high or high to low, the 6 speed. We are comparing with 2. For connection in series, when you connect two transistors in series, it's getting more difficult to conduct. It's just like if you connect a resistor and connect two resistors in series, they have different resistance. Is that clear? From physics. When we connect the same resistor in series, the resistance, the value is double. So when the current goes through, it's getting more difficult. Okay? Given the same voltage, the current is going to be 1/2 because V over R is the current, right? That's the physics law. If R is higher, even the same voltage, current is going to be smaller. So we connect two resistors, the resistance is going to be double, the current is going to be 1/2. Meaning indicating that somehow it's more difficult to travel on the wire. Likewise, for the transistor, when you connect two transistors in series, you need to the switching speed becoming 1/2. I mean, it's going to take more time to turn on, to get it up to low. For connection in parallel, then you might wonder, well, then it should be 1/2, right? You connect the transistor to the resistance. like this. The resistance is going to be 1/2. If we connect in parallel. However, we are considering the worst case, meaning when P network is on, it could be only one PMOS transistor is on, the other one is off. So when you compare P and N, you should take only one PMOS transistor into account, into consideration, if this is parallel connection. So just imagine that, just cover one PMOS transistor. You only compare it, one PMOS and two NMOS in serial. You compare these two circuits to compare their switching speed. And when I said PMOS transistor, the electron hole mobility is only 1/2. But NMOS transistor, they're connected in serial. Eventually, they are equivalent to each other. Right? Even one PMOS and one NMOS, even the same size, the same channel width. PMOS is more difficult, is slower to turn on. NMOS is easier, is faster to turn on. However, if you connect two NMOS transistors in serial, it just compensates. It just becoming equivalent to PMOS and NMOS with the same size. Because we don't take into account the parallel connection, because only one PMOS can turn on the output. That's the worst case. Although it was not turned on, yes, the output is going to be switching faster, yes, but we only consider the worst case for 0 to high and high, 1 to 0. Yeah, we only consider the worst case. That's why we say that, okay, this is 1 and 1, 1. Any question? All right, and I'm going to give you another case to consider. How about this? And we're not going to talk about it today, but we'll discuss it this week. So please remind me to go back to visit for PMOS transistor in series. For NMOS transistor in parallel. Okay. Now we have again two input, two NMOS transistors in parallel and two PMOS transistors in series. Can you tell me what is the size of each transistor, such that the switching from low to high, from high to low, is about the same? And also try to make it as small as possible. Well, maybe I'm going to give you the answer right away, but I can try to simplify it at home. But I said, when you have connection in parallel, don't consider the parallel connection effect. Just cover the other, only one. You are considering the worst case, right? Worst case. Although both are on, it's going to be faster. But we consider worst case. So only consider one NMOS. And you're comparing two PMOS in series and one NMOS transistor. So what is the size? For switching speed, 0 to 1 and 1 to 0 are the same. But I said PMOS transistor need double the width. But again, they are also connected in serial. So it's going to be 1, 1, and 4. Okay? think about it. We can come back and discuss it this week. And please remind me. Okay, that's for today. And again, please go back home and watch the video again, because that's going to be covered in the exam. All right? 好，下课了。